former PhD student at the University of Genova. And the work builds up on some previous work done by Francesca Campi and Marco Pelassa, who were also at the University of Genova. And the work is funded by the US Office of Naval Research and by the Italian MUOR. In my presentation today, I will start with a brief introduction to give you the motivations for what we are doing. I will then present a multi-scale structural model we developed to analyze the response of layered composite structures. And I will show you an application of this model to investigate mode 2 dominant brittle delamination fracture in layered systems. Now, modeling the response both in the elastic and in the post-elastic regime of layered composite is quite challenging for many reasons. And I want to point your attention on these two reasons. The first is the inhomogeneity of the material structure. And the second is the fact that the post-elastic regime is dominated by the growth, evolution, and interaction of multiple damage mechanisms. So I want to discuss a little bit these 2 points, showing you some diagrams. So here you see some in-plane displacement, bending stresses, and transverse shear stresses in a 3-layer plate, a thick plate subjected to this sinusoidal load and under plane strain condition. This is an exact elasticity solution of the problem, and the layers are essentially 0, 90, 0 layers. And you can see that the displacement field is nonlinear and has this very well-known zigzag pattern. So this tells us that in this material, a linear displacement, which is what we get using the classical equivalent single-layer theory, does not describe the response of the actual material. And you also see that the transverse shear stresses and the bending stresses have this complex distribution. And if we now account from the presence of some imperfection between the layers, this solution was for fully bonded layers. And if we now introduce some sort of tangential springs between the layers, and these are linear spring with stiffness K, then, as you can see, the response changes substantially. And in addition to the zigzag pattern, we also have jumps in the displacement and the layer interfaces. And as you can see, shear stresses and bending stresses changes substantially. So in the presence of imperfection, the response changes substantially. And we need to be able to describe with our model these stresses, because those are the stresses that will initiate and the condition for crack propagation in the system. This is another effect which I want to discuss with you, and is the interaction of multiple delaminations. This is a load deflection diagram, and is the result of some experimental tests performed by Robinson many years ago. So he tested this double cantilever beam with 2 implanted delaminations. And here you see that the response has these local instabilities, a snapback and a snap-through instability, which are a consequence of the interaction of the delamination. So when the 2 crack tips come close to each other, they interact, and there is important phenomena of amplification and shielding of the local fields. And this phenomena may generate snapback and snap-through instability. They may induce accelerated growth of crack. They may even arrest crack propagation. And obviously, we want our model to be able to predict this kind of behaviors. So the classical modeling approach to study layered system in the post-elastic regime is discretizing the structure into layers, thin layers, and using cohesive interfaces between the layer in order to describe the intact regions of the plate and the propagation and evolution of multiple delamination. This approach has a number of drawbacks, obviously. And first of all, we cannot obtain closed-form solution. We can have closed-form solution just for very simple problem, and therefore we are losing the insight of the closed-form solution. The computational modeling is quite cumbersome, and also we need very fine meshes in order to be able to describe the local field and all the effects I just presented. So a few years ago, we then decided to propose a different approach to analyze layered system, And our idea is essentially to try and remove the need for a true thickness discretization of the problem. And by doing this, as we will see, we are able to get closed form solution for an extended range of problems. And when we implement this approach into a computational model, we also improve the efficiency of the solution. Now, these slides summarize our model, which is a multi-scale approach. And what we do, we want to couple two different models at two different scales. At the global scale, we consider an equivalent single-layer theory. We have been using first-order shear deformation theory and first-order shear, first-order normal deformation theory. And both models are described by a limited number of variables, between 3 and 6, depending on the geometry and the assumption you make. And these models are well known in the literature, and they can describe the global response of the plate, of the layer plate, nicely. But obviously, they cannot describe the local fields and the phenomena I showed you before. So to describe those fields, we use a local model. So at the local scale, we use a very classical discrete layer cohesive crack model. So in this model, we discretize the plates into layers, and we introduce cohesive interfaces, which are governed by cohesive traction law. And obviously, this model has a large number of variables, which depend on the number of layers. So the idea is to couple these two models using a homogenization technique in order to obtain the small-scale variable as function of the global variables. And then we can apply a variational technique, and then we will obtain the equilibrium equation of the problem, which are in terms of the global variables only. Now, I'm not going to show you the mathematical detail, given the time of the day. I just want to focus a little bit more on the main assumption of our model. So we essentially extended the original theory developed by Deschuva, the zigzag theory, for fully bonded layer plate. And the idea is shown here. So this is a 4-layer system, and this is the zigzag displacement field. And we assume that the displacement field is described by these 3 different contributions. The global field, which is the field of our global model, the coarse-grained model, so equivalent single-layer theory. And then we add some local perturbation, a piecewise linear field in order to describe the zigzag behavior and the inhomogeneous material structure, and a discontinuous field with jumps at the layer interfaces to account for the presence of delamination and imperfect interfaces. Obviously, the number of variables is very large, but as I said, we can use a homogenization technique, and what we do, we impose continuity of normal and shear tractions at the layer interfaces, and by doing this, we can obtain the local variables as function of the global variables. Then we use a variational technique, and we get the equation of the problem, the equilibrium equation. I'm skipping all the equation for the sake of time, but I can show them later if you're interested. So this is to show you how the model works. So I reproduce with our homogenized model the plate I discussed before. So it's a 3-layer thick plate with a 090 layup. And here you see in-plane displacement, shear stresses and bending stresses. The first row is the fully bonded layer. The last row is the fully debonded layer. So all layers are fully debonded. And this intermediate row is a partial bonding between the layers. You see how well the model reproduces the zigzag pattern in the displacement, the jumps at the layer interfaces, and how well it also reproduces the complex stress distribution, transverse shears, and bending stresses. And we can do this with just 3 displacement variables. So essentially, to solve this problem, we are using equations which are similar to Timoshenko-Beam theory. So just a very simple equation that we can solve in closed form and get this kind of behavior. And here is another example. Now, the idea is to extend this approach in order to analyze delamination evolution in the system. And the focus of my presentation today is only on mode 2 dominant fracture problem, on a problem in cylindrical bending or beams problem. And we are therefore assuming the interfaces to be just sliding all the interfaces. So this is a layered beam with many delamination and many layers. And the layers are joined by cohesive interfaces, and we use this cohesive interface traction law in order to describe both the intact part of the specimen and the delaminated part. We apply our homogenization technique, and this is the equivalent homogenized beam, in which, as you can see, we don't have any need to describe, to discretize in the true thickness direction. So each region of this beam will be described by the equilibrium equation we derived before, and we have closed form solution for each portion of the beam. And let me show you some application of this idea. So this is an application of the model to a unidirectionally reinforced ENF specimen. So the material is essentially homogeneous, and we have a crack which is a mid-thickness. We homogenize the model, and this is the homogenized beam, and we derive in closed form the energy release rate, the mode 2 energy release rate. And this is the equation we get. This is the same solution we would get using a structural mechanics approach, a classical discrete layer model. And the solution captured the dominant terms of the exacto to the elasticity solution. What is missing here are these additional terms, which are less important because they are either constant or are a linear function of the crack length. So they are important only for short and intermediate crack lengths. And they are due to the near tip deformations, which are neglected in the homogeneous material in our model. And this is an application of the model to reproduce some experimental tests on graphite epoxy, on a graphite epoxy laminate. The tests were conducted again with the ENF geometry. The blue curves are the experimental result published in this paper, and the black and red curves are the solution of our model. The two different curves have been obtained using the maximum or the average parameter given in the experimental paper for energy, fracture energy, and material properties. And you can see how well the model described the unstable propagation of the crack, which was not captured in the experimental tests because they were under displacement control. And again, we are using a model which uses the same equation essentially of a beam theory model. And here is an application of the model to a layer system. This is a symmetric sandwich with a deep bond between the two upper layers. And this is the critical load for the propagation of the crack in the specimen as function of crack length. And we are comparing our solution with an exact elasticity solution. As you can see, the results are extremely good, even for very short crack length. And the reason is that this crack is indeed propagating under mode 2 dominant condition. The phase angle is 83 degrees. And the model is also able to capture the effect of the inhomogeneous structure. So the black curve here are obtained for the same specimen with the same delamination crack at the same height. But in this case, the material is assumed to be homogeneous. And you can see that the critical load for crack propagation changes. And the model will capture again the exact elasticity solution, which is shown here by this dashed line. And finally, and this is my last slide, we have been applying this homogenized model to analyze the evolution of a system of multiple delamination. So what we did, we considered this cantilever beam with two initial delamination at different positions in the beam, and we followed the evolution of the delamination in the specimen, and you see that our model was able to capture these local instabilities and these local phenomena which occur due to the interaction between the different delaminations. The results here are compared with the result of a classical discrete layer cohesive crack model, and these are results we obtained quite a few years ago. So as you can see, we are even able to follow the evolution of crack and to follow the interaction, predict the interaction between cracks, again, using a model which has no need for true thickness discretization, and equations which are very similar to those of beam theory. So with this I conclude. So if I can read it, I do have that? Okay. So we have been using a homogenized structural model to study mode 2 dominant delamination fracture in layer beam. The delaminated beam is modeled as an equivalent homogenized beam, so we have no need for a true thickness discretization of the problem. The energy release rate can be defined in closed form for a number of problems. The model is able to capture the effect of the multi-layer structure on energy release rate and critical load, and is able to follow the unstable propagation of the crack to predict local instabilities and the effect of the interaction of multiple cracks. Thank you.
Thank you.